Hello everyone. Today we are going to discuss WKB approximation method. So here WKB three scientists Winchell, Kermers and Brilliance. So this approximation technique obtaining approximation solution for one-dimensional motion of a single particle by using Schrodinger wave equation. And WKB method demonstrate the connection between the classical quantum theory and quantum mechanics. So simply I can say the in terms of h power 0, h power 1 and higher order terms. So this method is useful for systems with a slow varying potential, slowly varying potential. That means the potential which remains almost constant over a region of order of de Broglie wavelengths. For example, this is one system. This is slowly varying potential with the first displacement x. In next, after some times variation, the system goes to dx position. Here, this dx is the in the region of order of almost constant in the region of the order of de Broglie wavelength. This property almost satisfy in the case of classical systems, since the wavelength of classical systems approximate zero, which is why this method WKB approximation method is also called a semi-classical approximation method. So general formalism of this WKB approximation method, consider a particle of mass m and the particle in a time independent potential. For example, if I take V of x is time independent potential, Schrodinger equation for corresponding states are minus h cross square divided by 2m L square psi plus V of x psi of x equal to E psi. Here the psi is a function of x position. Okay. So this is our Schrodinger wave equation. So I'm going to use this term is a gamma square, right? Gamma square equal to the 2m h cross square E minus V. Here this term gamma is the classical momentum. Remember this one is the momentum. I'm not saying that momentum mass into velocity directly. So this is a on momentum particles, gamma particle. Okay. If particle is moving a region where V of x is almost constant, in that case, the solution of the Schrodinger wave equation is psi of x equal to a e exponential plus or minus I gamma x divided by h cross. So in this solution, this is systems having constant potential. What happen if the systems varying, I mean slowly varying potential? Let us assume on trial wave function for satisfying equation number one. This is our Schrodinger equation, right? This is our Schrodinger equation. So here I'm going to use one trial wave function. So this is our trial wave function in SNC case. This is our trial wave function I am using here. These two are not similar solutions. Okay. So it considers trial wave function to satisfy the equation number one. Here I'm using one solution, trial wave function. J of x is equal to ax exponential I. S is a function of x divided by h cross square, where the A is the amplitude, S is a phase. So please carefully here the A is the amplitude, S is the phase. So next few minutes we are going to solve this. What is the amplitude of the system? What is the phase of the system? That's it. Then we will look into the where this equation is going to fit in our solutions. Okay. So here the A and S are the real functions. So now I'm going to substitute this trial solution. I mean this trial wave function. Here I'm using trial wave function like this. A exponential I S divided by H cross. Substitute this equation 2 in our Schrodinger equation, in this equation. So then try to simplify this equation carefully. So if you substitute this Schrodinger equation, you'll get the first solution, because d square psi by dx square plus gamma square divided by h cross square into wave function psi is equal to 0. So in place of wave function, I am going to substitute our trial wave function, right? So if you differentiate this term only, two terms with respect to x, so I got this equation. Again, I am going to derive this entire equation with respect to x. Will expand this equation like this. Okay. Next step, what I did here. So just simplify this equation carefully. Then we will get the simplest terms like this. This is our simplest terms. Then you rearrange this equation in terms of IH cross terms separately, I mean imaginary terms separately, real terms separately. Suppose you will get this type of equation. This is our real term in under this equation. Okay. This is our imaginary term. The real term and imaginary terms must vanish separately. Okay. So neglect h cross square term. Here, whatever h cross square higher terms are there, you can neglect. Remaining terms you can use in our solution. So here I'm going to look into simple explanation here. So what we considered first thing, suppose we are taking Schrodinger equation, the solution of Schrodinger equation, if potential is constant, if it is potential energy is constant, then this is our solution, well-known solution. For example, but how does the deal with in the case of the potential energy is not constant? The WKB gives the answer such type of systems. Okay. So entire discussion is, so here the potential energy is constant of the system. What happen if V of x, I mean potential energy is not constant? Answer is given by the WKB method. So the WKB method provides an approximation treatment for systems whose potential, while not constant, are slowly varying function of x. That is, V of x is almost constant in the region where they extends over several de Broglie wavelengths. So in this case only we are using this solution. Okay, trial solution. So after substituting this trial solution, equation number 1, then we can get uh, these equations. Okay, this is our equation, final equation after substituting a trial solution. Real terms and imaginary terms are there, so these two terms going to must vanish separately. Here I'm going to neglect higher order terms. So first here the real term, so this is the real term, right? Minus plus gamma square ax. So here a going to cancel, and ds divided by dx whole square equal to gamma square. We know already what is gamma square, 2m divided 2m e minus v, right? So simply substitute this one, then d divided by dx in terms of s equal to plus or minus root of 2m e. And then this dx will go here, so ds equal to plus or minus root of 2m e. Then I want only s phase. Okay, so integration differentiation cancel, then s equal to plus or minus root of 2m e minus v into dx I got. So this is my s. Okay, so in our system, if you look into our solution here, this is our solution. So if you substitute this solution in equation number 1, what will get? Amplitude and phase we will get. So first term I got s. Okay, phase I got. So if you compared these imaginary terms, this is our imaginary term. Okay, see here. So imaginary term is 2 del A del S A del square S. Okay, so this is also going to must vanish. Then I rearrange this equation like this. I hope you understand this one solution. So here the A square S prime equal to C square, the constant. Then A equal to, this is our solution. Amplitude equal to some constant C divided by root gamma. Then substitute equation number 3 and 4 in equation number 2. You will get this equation, right? So this is our final solution. So here two cases are there. One is what happen if E greater than V of X. Let us consider the case this one, E greater than V of X, which is called the classical allowed region in our slowly varying potentials. So this is our system. For example, these are two boundary conditions. X2, this is X1. Okay, one is what happen if this is a dot line is energy, right? So energy is greater than the potential energy. So we already know it is a particle is easily penetrate through the barrier, the classically allowed region. In that case, this is the solution. So this is our solution, right? Here the C plus divided by root gamma x is the exponential term plus C minus root of gamma is a function of x here also, exponential minus I divided by h cross root of gamma of x dx. Second case is very important, this one here. Second case is E less than V of x. Classically, it is not possible to penetrate energy into the barrier, but quantum mechanically, it is possible. So in that case, the classically forbidden region is This is the solution. We already familiar this type of cases. Many problems we solved using approximation solution, one dimension Schrodinger verification, potential wells, potential barriers. We already seen this type of cases here. So in this equation, if you mentioned the equation number 5 and 6 here, the exponential term is imaginary in equation 6, exponential term is real in equation number 6. Case 3 here, very important case here. So here equation number 5 and equation number 6 gives the system's wave functions in the allowed and forbidden regions respectively. But what about the structure of wave function near the region where the for example energy is approximately equal to the almost equal to the potential energy. So what happened in this case? So energy is approximately equal to the potential energy. So at points x1 and x2, v of x almost equal to the energy. These points are called classically turning points because the classical particle stop at x1 and x2 and then return back to resume its motion in opposite direction. So therefore here gamma root of 2m e minus v. Here gamma equal to 0 momentum, so opposite direction for example. So what happen if this gamma equal to this 0? We know, right, lambda is equal to h divided by p, de Broglie wavelength, right? So if p equal to 0, lambda tends to the infinity. Anything divided by 0 is infinity, right? So lambda tends to infinity. The same like here, this is our solution. So this is momentum of the system. Okay, this is our momentum of the system. For example, c divided by 0, this wave function going to the infinity. Wave function going to the infinity. So then we are trying to find this values of WKB approximation, where this WKB approximation is valid. To obtain the condition of validity for WKB method, let us examine this equation like this. If you look into solution of our equations, there h cross square del square s less than modulus, this one is modulus, uh, del s whole square, this is double derivative, this is whole square, single derivative whole square. So simply here I am writing s double derivative, this is indicated as single derivative whole square. From our solutions, ds divided by dx equal to gamma. So where we write this one equation, if we find equation number 3 here, so this is equation number 3. Easily you'll get this equation, right? See here, ds divided by dx equal to, so this one is, what is this one? This one is gamma, right? So that's what I am using here exactly, gamma. So then this h cross I am using rearrange this equation like this: d by dx h cross divided by s prime less than 1. So then h cross divided by gamma less than 1. Here the h cross divided by gamma momentum equal to the lambda. This is the de Broglie wavelength. This condition clearly breaks down at classical turning points v equal to v of x. Next class, we will discuss what are the quantization rules of WKB approximation methods.